Humans have always been incredibly good at spreading out, right up until we hit a deep canyon or a fast-moving river. Suddenly, our expansion stops dead, and we're left staring across a massive gap. The earliest solution to this problem was simple material placement. By dropping a sturdy log or a flat slab of rock across the opening, we created the first beam bridges. Placing material over open air subjects it to a physical struggle. Gravity pulls straight down on the center, causing the material to bend. As the gap widens, the bridge becomes heavier. This added mass increases the load until the material snaps. To cross wider expanses, engineers stopped looking for larger materials and started developing new geometries to manipulate these invisible forces. The stone arch, perfected by ancient builders, provided the first major breakthrough in spanning large distances. The curve of the arch redirects that energy. It transforms the straight downward pull of gravity into compression, pushing structural blocks tightly together. This geometry guides the structure's weight along the curve, transferring it into the ground or supporting abutments on either side. While stone is excellent at handling compression, its high density created a weight limit. This mass restricted how far a single arch could stretch before it became structurally unstable. Mastering these compressive forces allowed empires to build durable roads and aqueducts that remained standing for centuries. During the Industrial Revolution, the demand for infrastructure shifted. Engineers needed to move heavy, vibrating locomotives across massive valleys and rivers. Traditional stone arches were too rigid and material-intensive to meet this new scale of transportation. The adoption of cast iron and steel introduced a new structural capability. Unlike stone, these metals withstand tension, the force of being pulled or stretched without fracturing. Using these metals, engineers developed the truss. This system of interlocking triangles distributes weight through a mix of compression and tension, allowing for a lightweight frame that can carry immense loads. Advanced geometries, like the cantilever, allowed builders to extend heavy steel spans over deep water without needing temporary support pillars at the center. This combination of high-strength steel and triangular geometry removed the limitations of sheer mass, enabling the construction of the global rail and road networks we use today. Some geographic barriers, like deep ocean straits, make it impossible to build any foundation on the seafloor. Suspension bridges solve this by hanging the entire roadway from overhead steel cables. The weight of the deck travels up through vertical suspender cables into the main suspension lines, which then drive that entire load directly down into the primary support towers. These ultra-long, lightweight spans are highly susceptible to torsion. Crosswinds can cause the deck to twist and oscillate. Ignoring the aerodynamic effects of wind on these structures led to catastrophic failures, where the roadway twisted until the steel and concrete reached breaking point. Megaspan construction demonstrates that as bridges reach extreme distances, the engineering priority moves from supporting static weight to surviving the dynamic chaos of the atmosphere. Modern megastructures function as highly tuned systems. They rely on active responses to external conditions to maintain their stability. Digital sensors now monitor micro-movements, temperature changes, and traffic loads in real time, allowing the structure to flex and adapt to its environment. The progression from simple wooden beams to these sensor-laden cables marks a transition from basic material substitution to the sophisticated management of physical forces. Every crossing is a journey through a massive, active mathematical equation that keeps the roadway stable against the combined forces of gravity and wind.